component. And well, I mean, this is one of the area which I got interested few years back, and yeah, still I'm continuing in this one. That is one of my research interests. And yeah, things are not very difficult, but I think they are nice, cute, and I think it has several applications also which are coming up, and that's what I thought that let me uh, pick up this topic. Okay, this is more or less the outline of my talk. First, we'll start with some motivations. I mean that the kind of data what can be analyzed. I mean, well, I mean why this kind of model is needed for that, and then I'll be talking about some of the specific model. I mean, one of the first one is, of course, the most famous one, the Marshall-Olkin bivariate exponential. An extension of that is Marshall-Olkin bivariate Weibull, and then bivariate generalized exponential. And then at the end, which is a recent work actually, which currently I am working on, and well, it is still under preparations, which is a general constructions where all these things can be taken as special cases actually. Okay, so yeah, so let's look at a couple of data, rather a couple of different types of data which we are interested in. Okay, so this is one of the data, I mean, which is this is data. I mean, this is the soccer data actually, football data. By the way, this kind of data which are very much available. I mean, I don't know how many of you are familiar with. I mean, these particularly if you look at this European Premier League, or if you look at particularly the UK League. Here you can see this one that they have these lots of these data which are available, and these are mainly for actually commercial purposes. I mean, it is not only not only for the entertainment. I mean, it is not only for the I would say these academic purposes. Actually, they have lots of these commercial purposes also, because many of these TV channels they try to analyze this kind of data, and depending on that, they actually promote this kind of game and that all these things. Okay, so this is one simple data which said that the two teams, of course, they're playing the soccer, and what we have recorded that the first goal which is scored by the home team and the first goal which is scored by the opponent. So one thing is clear, this is those kind of data which have been collected here, where both the teams at least score one goal each. Okay, so we have a home team and the opponent. So you can see that 5.35 minutes, 35.43 minutes, and things like that. Okay. Let's look at the data set 2, which is a slightly different one. And the data set 2 actually gives you the first column, which gives you the at which the home team scored the first goal, which is there. And the second number indicates that the time at which the first kick goal took place. And what is the kick goal basically means? The kick goal basically is the free kick, corner kick, penalty kick took place. And so the natural question asked that why somebody is interested, and actually somebody is interested, particularly the TV channels. They are interested this kind of goal because these are quite spectacular. I mean, it is people usually like to watch those kind of goal, particularly if it's a free kick goal, corner kick, penalty kick, and things like that. And people do like to watch these things. Okay, so you can see that if you look at the first row, which is the home team 5.35, and the kick goal 5.35, so which is very, very clear that the home team scored the first goal and it was a kick goal. Okay, that is very, very clear. Whereas in the second one, if you see that it is a 23.65 and 12.24, so it is very clear that the home team scored the first goal as 23.65, and the kick goal took place, the first kick goal took place as 12.24. So clearly it was by the opponent who scored before than the home team, which is a kick goal, and which is the at the 12.24 and things like that. Okay, so we have two different data sets. and both the data sets indicate the time the first goal took place, but that they are the two different types of data sets. Now, what is the major differences? So, I mean, one thing is clear that both the marginals are continuous. I mean, well, I mean, I can take this one as a continuous one. I mean, looking at the seconds and all these things. So you can take it as a continuous one. But in the first case, clearly there cannot be any ties because the two different sides are scoring the goal. So clearly there cannot be ties. Whereas therefore the usual bivariate distribution, whereas in the second case there is a positive probability of ties clearly, because if you look at the second case where the home team 5.35 and the key goal is 5.35, so clearly there is a positive probability that there are ties. Okay, so therefore the usual bivariate distributions, basically what we are familiar with the absolute continuous joint probability density function, may not be used to analyze this kind of data sets. Okay, so that is very clear. Let's look at another data sets. Suppose we have the following data from major cities in India, which basically the first one indicates the minimum temperature on a particular date, so November 2nd, and the average and the minimum temperature of November 2 of this particular year. So again, clearly, because of the truncation, in the sense, suppose I took it up to maybe say 1 decimal point or maybe 0 decimal point, clearly, because of the truncation, there is a positive probability of ties. Okay, so that means clearly the today's temperature can be the average temperature on that particular day. So clearly, there is a positive probability of ties. Okay, so these are the things. I mean, the reason I'm mentioning these things that, well, the usual bivariate distributions which are absolutely continuous, those cannot be used to analyze this kind of data sets. Let's look at another one, which is actually a dependent computing this data. This is one of the data set which is available, which basically gives you. It has been taken it from I think this I hospital from, I forgot exactly the name, but anyway, the major study what they are trying to do it here, they are trying to see that what kind of effect this laser treatment has on the glaucoma patients, in the sense that whether this laser treatment which can delay the blindness on the glaucoma patients. Okay, so that's what it is. So the way this experiment was conducted, that at the beginning of the experiment, for each patient, I mean those were among the glaucoma patients, they choose one of the eye at random, and they give the laser treatment, and for some I mean, yeah, they give one of the eye to the laser treatment, and then they look at that what is the time it takes becomes a blind, and they are recording those things, and the data basically the minimum time to blindness t, and the indicator specifying whether it is a treated eye, in the sense whether it's a laser treatment has been given to that eye, or the untreated eye, or both the eyes. Okay, so it is basically the data which looks like this, that the first one basically indicate that the 266, this is actually in days, and then it is delta is equal to 1, which basically means the treated eye, that means that this is the laser treatment was given to this one, and it becomes blind after this one. Similarly, the 91, 2. And what is important here, that if you look at the third one, which is 285, 3, that means this 3 basically indicates that both the eyes become blind at the same time. Okay, so there are ties again. In fact, in this data set, there are significant amount of ties, in the sense that both the eyes become blind at the same time. Okay, so these are the type of data we are looking for. I mean, we are basically trying to see where the usual bivariate distributions cannot be used directly to analyze this kind of data. Okay. So these are the some of the standard, very standard, absolute continuous bivariate distribution. Need not be on the positive axis. It is, I mean, I'm taking it from on the entire real line. For example, the first one, of course, the most popular one, the bivariate normal, which is absolute continuous distribution over the entire R2. Similarly, we have bivariate log normal, which is of course on the only on the positive positive quadrant. Similarly, you have the bivariate inverse Gaussian distribution, that is also on the positive quadrant, and the bivariate Bernoulli-Saunders, which is also on the positive quadrant. So these are some of the very, very standard ones which have been used for analyzing bivariate distributions, which are absolutely continuous. Okay. So, but again, as I mentioned, that these are the things which cannot be used to analyze this kind of data, because in all these cases, there is a zero probability that probability x is equal to 1. Okay, so I think this is the first one, as far as I know. The Marshall-Olkin bivariate exponential distribution is the first one which was introduced to take care that when there is a positive probability of a bivariate distribution such that probability x is equal to 1 has a positive probability. There are mainly two approaches what I have found. One is, of course, the minimization approach, which was the famous one by Marshall-Olkin way back in 1967, came out in JASA. But I mean, most of the distributions which was available, it was based on the minimization one. But in 2009, the maximization approach also comes into picture. Yeah, so that is also there. So I have seen these are the mainly two main approaches. There are certain variations from these two, but these are the main this kind of IVP distributions. Okay, so yeah, let me give the definition of this Marshall-Olkin bivariate exponential. It was first introduced, and it starts with 3 independent exponential random variables with parameters lambda 1, lambda 2, lambda 3, and let me just put this the exponential distribution. This other form also, but here I'll be sticking to this particular one, which basically means that the mean function, and that is the distribution function what we have. Okay, and as I said, it's a very simple one, very simple way. You introduce this Marshall-Olkin bivariate exponential, which is basically the minimum of x1 and x3, and y is equal to the minimum of x2 and x3. Okay, so so the bivariate distribution is xy. So because of the introduction of this x3, you can see that so they are, although x1, x2, x3 are independent, but x and y they are becoming okay. So you can it has a very, very interesting physical interpretations, and that's what this Marshall-Olkin has pointed out. And that's the reason that this particular model is also called the shock model, because it has a nice interpretations of shocks. And what it says, this one, that suppose the shocks comes according to the Poisson process, and the first shocks appear affect the component 1, the second one affects the component 2, and the third one affects both the components. Okay, so basically I have 3 different the shocks can come. The first one affect the component 1, the second one the component 2, and the third one both the components. And the component fails as soon as it receives the shock. Okay, so that's what it is. So therefore, what you can see this one, that if x1, x2, and x3 they denote the time. They are all continuous time, by the way. They denote the time at which the first shock, the second shock, and the third shock arrives. Therefore, the lifetime of the component 1, which is the minimum of x1 and x3, and the lifetime of the component 2, which is the minimum of x2 and x3. Okay, so basically, you can see this one that the component 1 and the component 2, they have the lifetime x and y, and because that the first one, the x1 can affect the first of x1 affects the component 1, and the x2 affects the component 2, and x3 affects both, and simply like minimum of the x1 and x3, and the minimum of the x2 and x3. Okay, so from here we can easily compute what is the probability that x is equal to y. But before that, we can easily see that because of the minimum one, because since it's a simple model exponential, it's a minimum one. So x becomes exponential with parameter lambda 1 plus lambda 3. Y also becomes exponential with parameter lambda 2 plus lambda 3. And the minimum of the xi, which is exponential with parameter lambda 1 plus lambda 2 plus, is a very simple one. Okay. So if you look at the probability x is equal to y, as I was saying this one, that probability x is equal to y, which is simply, of course, it's a very simple one, that the minimum. So that means that x is equal to y, it has to be x3 because, both of them are equal. So therefore, your x3 has to be less than x1, your x3 has to be less than x2, and that's what is going to happen here. That the probability that x1 is greater than x3 and the x2 is greater than x3, which basically means that x3 has to be less than minimum of x1 and x2, and which simply comes out to be lambda 3 divided by lambda 1 plus lambda 2 plus lambda 2, which is a positive probability, and that's what basically what you want. Okay, so probability x is equal to y, which is positive. And if you look at the survival function, which is again is quite simple to compute, and we are looking at the probability x greater than x and y greater than y, and which simply turns out to be in this form, that e to the power negative this one, e to the power negative lambda 1 plus lambda 3 x minus lambda 2 y, and lambda 1 x this one, if y less than or equal to x and y greater than x. So basically, if you look at this line x is equal to y, so if it is x is less than y, it is taking one particular form because of this maximum term, and if it is x is greater than or equal to y, it takes another form. And of course, from the joint survival function, you can easily obtain the joint distribution function also. That's not a problem. So let's come back to this, the basic thing that, well, the absolute continuity of this, the CDF or the survival function, which simply means that, well, I have a functions in two variables f of uv, such that I should be able to write this joint distribution function in this form, or the joint survival function in this. That's a standard one. So if there exists this function f such that the distribution function can be written in that form, and the survival function can be written in that form, then I'll call this one as the it is an absolutely continuous survival function, or the absolutely continuous distribution function. And of course, this joint density function I should be able to obtain from the joint survival function or the joint distribution function by simply taking the double derivative, nothing more than that. So let's look at, in this particular case, in our case, what turns out to be the joint density function. So if you're simply taking the double derivative of the survival function, it turns out to be this f of x lambda 1 plus lambda 3. So these are all basically the exponential density function, which I had already given there. It is simply nothing but lambda 1 plus lambda 3 e to the power negative lambda 1 plus lambda 3 x, and this is lambda 2 e to the power negative lambda 2 y. So for y less than or equal to x, it turns out to be the first one, and for y greater than x, it turns out to be the second one. Now, if it is a proper density function, so the whole integration should come out to be 1. So if you look at this integration, double integrations f of x y dx dy, from minus infinity to infinity, minus infinity to infinity, it's a simple calculations. It shows you that when it turns out to be lambda 1 plus lambda 2 divided by lambda 1 plus lambda 2 plus lambda 3, but which is less than 1. Okay, so which is not 1. So that basically tells you that, well, it is not an absolute continuous distribution function. Okay. So therefore, the usual notion of the joint density function does not exist in this particular case. But well, we can still interpret this one that suppose we basically the whole problem occurs because there is a positive mass on x is equal to y. Okay, so basically what we can do that we can still write down as a joint density function, and of course it is not with respect to the two-dimensional Lebesgue measure on the entire xy plane. It is basically a two-dimensional Lebesgue measure on the plane on the plane x less than y and x greater than y, but on the x is equal to y, I have a one-dimensional Lebesgue measure. With respect to that, I have this particular joint density function. Okay, so that's what, whenever I am talking about the joint density function, that's what it means. Okay, and but again, I mean, I can get the distribution functions simply by integrating this quantity or the survival function by this way. So that's what it is, the joint density function, which basically x greater than y, which is also two-dimensional component, but there is a one-dimensional component on the line x is equal to y. That's what it is. Okay. So that's what the joint density function means. So it is not in the usual sense because the usual one is with respect to the two-dimensional Lebesgue measure on the entire plane, but it is here. It is not that. Okay. So that's what we have. Okay. So this is a simple curve. I mean, simply the two-dimensional plot. What I had plotted the absolute continuous part of the Marshall-Olkin Bivariate exponential, and so because of this exponential nature, it will be always as a decreasing function. Okay, the plot has to be always like this because the exponential density function, I know that that it is a decreasing function. Okay, so I cannot get any other shape for the in case of the Marshall-Olkin Bivariate exponential. It will be always in this shape. Okay, of course the value at the point 0, 0, it can differ depending on the value of lambda 1, lambda 2, but the shape will be always like this. Okay, so a couple of interesting things. I mean, if you're looking at the survival function, it can always write it. I mean, by the standard notion that I should be able to write it as the absolute continuous part and the singular part. So the survival function can be written as an absolute continuous part and the singular part, which is a convex combination of the two. And the singular component, which is simply nothing but on the line x is equal to y, that's what it is. So that's what it is, that this quantity an exponential one, and the absolute continuous part I can get it by simply by subtraction. Okay, so the absolute continuous part and the singular part can be obtained, and the same way I can write the joint PDF also. Joint PDF also as a convex combination of the absolute continuous PDF and the survival the singular component PDF, which is again on the line x is equal to y, and the other one is the absolute continuous part, which is on the surface x less than y and x greater than y. Okay, a couple of things which are important for a bivariate distribution. When you're looking at this, the joint distribution or bivariate distribution, one important thing is that what kind of the correlations the distribution can have. So you can see this one, that if you take this lambda 3 goes to 0, then probability x is equal to y, that becomes goes to 0. So probability x is equal to y, that turns out to be probability x is equal to y becomes equal to 0. So actually it becomes the absolute continuous distribution function. And in fact, as lambda 3 goes to infinity, the probability x is equal to y goes towards 1. So in fact, in this particular case, the correlations between the two random variables x and y, they can always lie between 0 and 1. So the correlation here can never be negative. Okay, so that is one of the things which are the drawback of this kind of distribution, that well, the correlations are always strictly positive. Okay. This is one thing which is a much more general one. I can put it into that. I mean the copula. So this copula, I think those are familiar with. I mean it's a bivariate distribution functions defined on the entire two-dimensional surface for any bivariate distribution functions. I should be able to write this that joint distribution function as a copula function C, and this capital Fx and capital Fy. These are the marginals basically. Okay. So this is an unique representation. Okay. So for any bivariate distribution function, for at least for an continuous marginal, for the continuous marginal for any bivariate distribution function, I should be able to write it in this form. Here, this C, capital C, which is a what we call as a copula, which is actually simply nothing but a distribution function on 0, 1 cross 0, 1. Okay, so it is basically a bivariate distribution function on 0, 1 cross 0, 1. So any bivariate distribution has an unique representation as C of the marginals of the two. So basically, that's the decompositions what we have, and it is always turns out to be very, very useful that for many purposes. Okay. And if you try to recover the copula, which has this simple formula that, well, I mean, you try to get this one, the C of UV, that f of xy, which is fx inverse and the fy inverse. And that's the reason that you can see that makes it unique, because as long as your fx and fy are absolutely continuous, then no problem at all. Then you can have this fx inverse and the fy inverse. They are unique, and that makes that capital C unique. And we have a similar thing. Well, these are some of the simple example of the copula that which are the very, very standard one. And the C of UV, which is UV, of course, this is the most trivial copula because that gives you U and V to be independent. This is another copula, which are some of the simple copula what we have in practice. But let's look at, in this particular case, for that we need what we call as the survival copula. I mean, which is the same thing. That means that the way we have written the joint distribution function, we should be able to write it, the joint survival function also, along the same manner. And that's what we have done. The joint survival function S of xy, again, it has this unique representation C tilde, Sxx and Syy, which are the marginal survival functions. And again, I should be able to recover this C tilde from the survival function in this manner. Okay, so one thing you have to keep it in mind, this C tilde is also a copula in the sense that it is also a distribution function, by the way. Okay, same thing like the copula, and there is a nice relation between the copula and the survival copula for the same distribution function. For the same distribution function, the copula and the survival copula has this relation. Okay, so that means if we know the copula, I should be able to find out the survival copula and the other way. Okay, so basically, using this, I should be able to write down the joint survival function and the joint distribution function. I mean, it basically comes from there. So in this particular case, in case of the Marshall-Olkin one, well, I mean, I'll come back to this one, but it has lots of this usefulness actually, because it has many properties which are given invariant. If the two distribution functions have the same copula, then many properties given invariant. Then, of course, for a given copula, I can generate thousands of distributions. That is one. And the third one is that estimation becomes easier. And actually, that is one of the reasons the copula becomes extremely useful, because particularly for the high dimensional data, when I'm looking at a multivariate data with a very high dimension, if we use a copula, actually the estimation becomes much easier compared to that if you want to deal all of them simultaneously. For example, the maximum likelihood estimators and all these things might be much more difficult rather than using, if you try to use the copula structure and then try to use the parameters using the copula structure. Anyway, that's a different thing. But let's look at in this particular case, this Marshall-Olkin bivariate exponential has this survival function, which is in this form. And so therefore, if you look at this, the copula, which simply turns out to be this particular form, okay, which is a very simple to get. So this copula, C of UV, which can be written in this particular form. And so if we take this particular reparameterizations, alpha is equal to lambda 3 by lambda 1 plus lambda 3, and beta is equal to lambda 3 divided by lambda 2 plus lambda 3, this copula comes up. Okay, and this is known as the Marshall-Olkin Copula. Okay, and if you take alpha is equal to beta, that means if we take lambda 1 is equal to lambda 2, and if we take theta is equal to lambda 3 divided by lambda plus lambda 3, which the copula turns out to be a very, very simple, nice one. Okay, so and this is also known as the Marshall-Olkin Copula for a specific case. Okay. So again, I put these things because we will see this one later on. The other distributions, what we'll be talking about, they have the same copula actually. Okay. Okay. So let's look at this the Marshall-Olkin the bivariate variable, which is an extension of this Marshall-Olkin bivariate exponential, and which is a very, very natural extension. Although Marshall-Olkin did mention that one, but they did not work on it. But people have started working on it much later. And so this is the one, the Weibull distributions, what we'll be using it, which is basically the extension of the exponential. And so in this particular case, we go ahead and do exactly the same way what we did for the Marshall-Olkin bivariate exponential. We have done the Marshall-Olkin bivariate variable, where we are keeping these scale parameters as same as the exponential one, that means the lambda 1, lambda 2, lambda 3, but we are keeping the shape parameters same, okay? We are keeping it as alpha, and that's what it is. And now we define that x is equal to the minimum of x1 and x3, and y is equal to the minimum of x2 and x3. Okay? So that's the way, exactly the same way, we do that, okay? And this particular one has a nice interpretation in terms of the renewal process, because in case of the Marshall-Olkin bivariate exponential, that has an interpretation through the Poisson process. But here we have through the renewal process actually, and if you recall, the renewal process is basically defined along the same way. I mean, but here I'm looking at this Sn, which is summation of xi, where xi's are independent, identically distributed, non-negative, continuous random variable, and the counting process nt, which is basically defining through this maximum over n, such that Sn is less than or equal to t. And so if we take this xi's to be exponential, of course, it turns out to be the Poisson process. But if you look at xi's to be something else, then basically we have this renewal process. And in this particular case, what we have seen this one, that well, if you take this xi's to be viable, then actually this fits in quite well here. And so suppose you have a system, exactly the same interpretation, but instead of the Poisson process, we go through the independent renewal process, where this inter-arrival time are viable. Okay, that's what it happens, and it is exactly the same interpretation. That's, well, there are shocks, and the first shocks affect the component 1, the second shocks affect the component 2, and the third shocks affect the component, both the components. Okay, and the component fails as soon as it receives a shock. Okay, so it is exactly the same interpretation, but now the shocks are appearing not through the Poisson process, but it is coming through the renewal process, where the inter-arrival time of the renewal process, they are following the Weibull distribution. Okay, so that's the difference what we have. And as it is expected that it boils down to the Marshall-Olkin bivariate variable if you replace the YB by the exponential. Okay, the same thing. I'm looking at the lifetime of the component 1 and the lifetime of the component 2. x is equal to the minimum of x1 and x3, and y is equal to the minimum of x2 and x3. Okay, and same thing goes through that if you're looking at the survival function, which is exactly the same. Now it turns out to be this way. But again, if you're looking at the joint probability density function, which again in this tree form, one is the y less than x, and y greater than x, and x is equal to y. It is exactly in the same form as before, where the f1, which is again y loop, with the shape parameter alpha and the scale parameter lambda 1 plus lambda 3, and again, similar, exactly the similar one, just like the Marshall-Olkin Copula exponential. Okay, and these are some of the shapes what we can see for the absolute continuous part, and as it is expected that now I can have a different shape now. Okay, so I can have actually a nice unimodal surface also, so that of course much more useful for data analysis purposes. Okay, so this is basically the plot of the absolute continuous part, the surface plot of the absolute continuous part. Okay, what is important here that, well, I can have this again the copula, and in this particular case the copula is actually the same copula what we have in case of the Marshall-Olkin bivariate exponential. Okay, so it is exactly the same copula. So as I was mentioning, that the many properties, particularly many dependence properties between the two variables x and y, in case of the Marshall-Olkin bivariate exponential and the Marshall-Olkin bivariate y loop, they are same actually. Okay, many dependence properties they remain same, and not only dependence properties, actually many dependence quantity. Okay, so they are also remaining same actually because of this copula structure, because they have the same copula structure. Okay, there are three very important issues. One is, of course, the classical inference. What we have seen is one that this particular model has 4 parameters, and of course, if you are to go for the standard method, the maximal likelihood estimator, you have to solve the 4 nonlinear equations, and you have to the standard way. But well, I would not say that this is a very difficult problem. No, definitely not. I mean, it's now the 4-dimensional optimization is not a great deal, but still, I think we can have a very nice, easy, or I would say easy, but nice solutions through the EM algorithm, which actually involves only solving 1-dimensional optimization problem, which makes the life quite simple actually. Okay. Another one is the Bayesian one. Bayesian inference is also another interesting aspect in this particular case. And in fact, we can work with fairly flexible prior, which is basically the Dirichlet prior on the scale parameters, which are dependent. Okay, dependent prior what we can work on, and things can be carried out. And recently, actually, this model has been used analyzing these dependent computing this data, the data what I had mentioned, and people have used it. And actually, the people have developed this the classical inference for this dependent computing data. And yeah, yeah. So this can be used for that purpose. Okay. Now let's come to this the bivariate generalized exponential, and this is the one where this maximization process has been used, and this the bivariate generalized exponential, which is an extension of this the exponential distribution. If you recall, these Weibel distributions, gamma distributions, they are all extension of the exponential. This bivariate generalized exponential is also an extension of the exponential distribution, and which has a simple distribution function, which is given by this capital F of GE, and which has a simple density function, which is given by this one. And again, I can go ahead and do the same thing. I can develop the things x is equal to, instead of the minimum, I can work with the maximum now, which is the maximum of x1 and x3, and y is equal to the maximum of x2 and x3. Okay. So it is almost a similar one, but instead of the minimization process, we work with the maximization process actually. Okay, and well, as we had seen that in case of the Marshall-Olkin bivariate exponential and the Marshall-Olkin bivariate Weibull, we have interesting physical interpretation in terms of the shock model. And actually, in this particular case, it has a very nice interpretation in terms of the stress model or the maintenance model. And it can be described as follows. Say, for example, we have three different types of stress, and the first one affects the first component, the second one affects the second component, and the third one affects both the things. And the stress what we observe, which is the maximum of the two stresses for any component. Okay, so that's the reason that it can be interpreted as a stress model. Same thing with the maintenance model. I mean, you have a maintenance. If you've done one kind of a maintenance, the first one, second one, and both, and so it can be nicely interpreted as a maintenance model also. We can go through the same way. We can write down the joint distribution function, which is in this form, which is a very simple one. And again, the joint density functions along the same line we have in this one. And yeah, it is exactly the same thing. It has also the similar type of the shape of the absolute continuous part, similar to this Marshall-Olkin bivariate Weibull actually. Okay, these are the things. But another interesting thing is that if you're looking at the copula, in this particular case, we have this copula actually. Okay, which is a similar one, not exactly the same, but which is a similar one, like the Marshall-Olkin bivariate copula, but this one is slightly different one. And in this special case, if you write this way, the copula turns out to be this one, and yeah, so that's what it is. Okay. Again, I mean, here also this classical inference is an important one. Here also, actually, the EM algorithms can be developed quite nicely, which can be done. Bayesian inference, which has not been done, but I think definitely it can be done. Should not be too much of a problem. I think it can be developed. And again, this particular model, which actually has been used in analyzing the dependent, the complementary risk model. I don't know how many of you are familiar with this complementary risk model, which is not very popular, but I think again, it is available in the statistical literature, which basically gives you that you observe instead of the minimum, you observe the maximum. Okay, so that's what it is, and that's the reason that this particular model, which can be used, I mean, in analyzing the dependent, the complementary risk model. Okay. Okay. So now let's move to the general construction. As I said, I mean, this one I have started working on recently. I mean, it is, but all these things I think can be put together in a general framework, and yeah. So this is the one. So what we can do that. I mean, a bivariate and a variable xy is said to have a bivariate distribution with a singular component. I mean, that is basically our aim. That I just write it in the joint PDF in this particular form. Okay, so I have an absolute continuous part, and I have a singular. Okay, so that's the way I put it actually. Okay, so I just put any absolutely continuous distribution function and the singular component, which is in one dimension. And yes, as I said, that f of xy is a proper two-dimensional PDF, and the singular one is a proper one-dimensional PDF. And of course, it is the singular one which has a positive support only on the line x is equal to y, but otherwise it is zero. Okay, so that's the way it is. Okay, so that is a general construction. So what are the advantages? Okay, first of all, it can be very flexible, definitely, because you have a complete choice. You have a complete choice on this the absolute continuous part. You have a complete choice on the singular part. Okay, definitely it can be very flexible. But I think what is more important, which is that it can have the negative correlation also, because as I mentioned, in both these, the minimization approach or the maximization approach, if you're looking at the correlation between x and y, it is always actually non-negative. Okay, so it can vary between 0 to 1. Okay, but here I can have even the negative correlation also for a bivariate distribution. And how can we get this negative correlation? Negative correlation is very simple, because what I can do, I can choose my p. I can choose my p properly. I can choose my absolute continuous distribution function, and one of the simplest way I can do nowadays, again using the Gaussian copula, and I can stick in any distribution function there, so I can get a correlation over the entire range, and so therefore, in principle, I should be able to get all the whole range actually. Okay. Another thing is that I think this is also another important one. This multivariate generalization is also not difficult. I think I would like to mention one thing here. Although in all these cases, in case of the bivariate exponential, bivariate Weibull, bivariate generalized exponential, in fact all other bivariate distribution, it is not possible to, it is not difficult to generalize it to the multivariate case, because you follow the same process. But the problem what occurs is in the estimation. I mean, suppose you have the data, you have a multivariate data. So for example, maybe say p is equal to 4 or p is equal to 5, or even p is equal to say 3. Okay, suppose you have a trivariate data, and you want to fit this Marshall-Olkin bivariate exponential or the bivariate Weibull or whatever. What you need, you have to have data in all the sector, in the sense you have to have data on the sector that x is less than y less than z, x is greater than y greater than z, x is equal to y less than z, x is equal to y greater than z. All these things, all these cases, all these different cases, you need the data, at least one. Otherwise, the parameters are not estimated. Okay, so that is, I think, one of the major problems to use this model for the multivariate setup. Whereas in this particular case, if you're looking at this general one, it is not a problem at all, because depending on the data, you choose your model so that you are able to estimate. Okay, so that is one of the advantage. What I can see this one, that I should be able to, we should be able to do this. Okay, and well, I mean, of course, if you make it too flexible, of course, you cannot do much. So we put certain restrictions, and that's what actually we are trying to do. So that we are trying to make it continuous on the boundary in the sense of the x is equal to y. So those kind of restrictions we are trying to put it so that it resembles the well-known distributions, but it becomes more flexible than the existing. Okay, that's what basically we are trying to do. And I think with this, I'll stop it. And thank you very much. And yeah, I'll take any questions if you have. Yeah, please. Yes. How to get rid of?
Yeah, please. Please, you can ask any questions. Now you can unmute your audio and ask questions.
How to move out of this?
Louder, please.
Yeah, how to get rid of this full screen?
Dipan, can you help?
Yeah. Now I think it's okay.
Yeah, I think Alt F again should work.
Yeah, that's what I'm trying to do. yeah, that's okay. That's fine. Yeah, that's fine. Yeah. Okay. Yeah. Any questions or anything? Yeah. If anybody has.
You can ask your question.
Yeah. Please.
So there's a question from Deepak Prajapati. Please speak it out, Deepak.
Hello.
Hello. Yes.
Yeah. Sir, this MO coupler has positive dependence or negative dependence?
MO copula has a positive dependence.
Okay.
Marshall-Olkin Copula has a positive dependence. Yeah.
Okay.
It always has a positive dependence. Exactly. Yeah. It can.
I think a general observation, this bivariate generalized exponential is usually used for left censoring, and the Marshall-Olkin is used for random right censoring.
Yes. That is true. That is true. Yeah. And as I said, I mean, recently it has been used for this that dependence.
Complementary risk.
Yeah.
So Professor Jan wants to know, when is negative correlation possible?
No, that's what I said. That well, I mean, in this, if you look at this Marshall-Olkin bivariate exponential, bivariate Taubman, or the bivariate generalized exponential, they cannot have these negative correlations. But if you take this mixture approach, what I'm saying this one, that in this case it should not be any problem, because you can use any bivariate distribution in the absolute continuous part which has a negative correlation, which is possible. Okay, so using that, so as I mentioned, suppose we take a, say for example, Gaussian copula, okay, and you put some the marginal distribution, so naturally you can have your correlations which is negative actually. Okay, and you choose a proper p. Okay, so negative correlation is possible. That's what I'm trying to say. Yes.
So, any examples, Professor Kundu? Particular example?
Yeah, that's what I'm saying. I mean, you take the Marshall-Olkin bivariate. Sorry, you take this Gaussian copula. You take the Gaussian copula and maybe you stick to exponential distribution. That's it. You put the marginals as the exponential distribution. That should work. Okay, so take the Gaussian copula and put the exponential distribution as the marginal distribution. So that will have a negative correlation.
Okay, thank you.
Okay, that's what I said. Yeah, that's what I said actually. That should have a negative correlation.
Complementary risks is not as popular as the competing.
No, not at all. Actually, not at all. I think one of the problem what I have seen for the complementary risk, I mean, I think the first paper came by this J.K. Ghosh
Yes.
and Asit Basu.
I didn't.
Identified one, but I think one of the major problem is the data. I think that's what it is. I think that is one of the reasons that the complementary risk has a problem actually. I mean, only one place I have seen the data, which is one of these Bala student, Han, from Texas. Say he has a data set. I don't know from where did he get it. It is some data set what he has used for the complementary one. So so that data set, I mean, so at least I just see only one data set on the complementary risk, frankly speaking. I have not seen too many papers also on that, by the way. Yeah.
Would auction data kind of lead us to complementary risks, because there you're picking up the maximum? I don't know. Maybe we'll talk about.
No. In principle, many things should be possible. I mean, I see. For example, if you look at any parallel system, okay, if you're looking at any parallel system, but the thing is that, I mean, do you have a specific data? I mean, that's what basically you are looking for. I mean, that's what I'm saying. In principle, I mean, there should be many places it should be applicable. There should not be any problem. Many places, I mean, it should be there. But I do not find any data. See, you have a lots of this parallel. You have a suppose you have a parallel system. You have a data for the parallel system, but the complementary risk is something more than that.
More than
Because
that,
we
yes.
have, yes, exactly. You need to know the specific component also, which has failed later. Okay, so I mean both the things together will give you the complementary risk data. Otherwise, it is just a parallel system data. Okay, so that's what I'm saying. So for example, you have a huge amount of data for the competing risk, but you do not have that kind of a data for the complementary risk. That's what I'm trying to say. Yeah. Yes.
Any other question, please?
Yeah, just a reference. Hello, Professor Kundu.
Yes, please. Yeah.
I had just said a reference for dependent complementary risk model. I think Isha will send it to me, right?
It's not dependent complementary risks. I'll tell you about complementary risks and then we'll take it forward. So this is a paper by G. and Asit Basu, 1978, I think. I'll send you the details.
Yeah.
Oh, okay. Okay. Thank you.
So if there are no more questions, we can thank Professor Kundu.
Okay, good.
Thank you.
Thank you, everybody. Okay.
Thank you.
Yeah, thank you. And thanks, everyone.
Thank you. Okay, bye.
So I'm closing the session. Thanks.
Yeah, thank you.